All right, so welcome to the program. We're going to get started in approximately 1 minute. I'll tell you what's going on in the background. I am prepping, getting ready. I'm checking my stream health, making sure I've got a good, strong stream to the platforms that I'm going out to. I could be going to YouTube, Facebook, or LinkedIn, or I could be going to all three. I'm just making sure everything is working correctly. Audio looks good, all that jazz. Please don't forget to chat it up. There's a chat box, regardless of the platform that you're watching this on, whether it be YouTube, Facebook, or LinkedIn, you have the ability to enter your comments and your thoughts. Please be mindful everybody gets to see those, but share your knowledge because I think it will help the program. And watch that chat box because there's a lot of great information in there. And please send me ideas for the future programs. So it's about 1 minute, so we should be getting started. Thanks. Hey guys, everybody out there in YouTube land, LinkedIn land, and Facebook land, and Twitter land, and Instagram land. We're just getting ready, so give me a second, and we'll get everything rolling. All right, and there's Dan, who's just double. I'm gonna unmute you, and we're gonna do me with you. All right, there we go. And I spelt fake energy right. I had it as face energy before.
That works a little better.
Yeah, it works a little bit better. All right, so we are, I know what I want to do real quick. Just before we get started. Bear with me. There it is. I have to follow snooze, unfollow. Huh. Okay, turn on notifications, hide post, snooze, can't. All right. It looks like only people that I. All right, so we're live on all those channels. Okay, Daniel Carnovale. Welcome.
How you doing, Tom?
We're doing good, brother.
Yeah.
And this is not your first time. This is what this is only the second time you've been on the program, right?
Yeah, we talked about I think just power quality last time a little while ago, and Santino and Eric were on.
Yeah, that's right. Yeah. So you're at the Pittsburgh Experience Center. You were just down in Houston yesterday, right?
Yeah, we have both experience centers now are kind of trying to come together a little bit more and trying to build some of the similar demos. So we've been down there trying to pick some of the things up and do some pretty cool demos down there as well.
So why don't
We have a
you?
power quality lab like the one that we have up here, and so we can do stuff with harmonics and power factor correction and things like that.
Cool beans. So why don't you just remind everybody what you do, who you are, all that good stuff. Give us a little bit of
Yeah,
background.
so yeah, I've been in the field for a couple years. Back when I was first. Well, you and I sat next to each other in our PE exam.
That's right.
Remember that a while ago. But we, I've been doing power quality work since I first got out of college, and troubleshooting for problems in the field and things like that. And then I got into a new role here at Eaton a little while ago in marketing of all things. I got drafted into marketing as an engineer. I kind of pushed back a little bit, but I was found a way to make it pretty fun actually. So I kind of worked towards building this experience center here in Pittsburgh, and then again working with the one down in Houston now as well. But basically, my background is all around trying to troubleshoot power systems problems and create um, you know, application examples for people. And so one of the things that I got involved in a lot of was around this false energy savings thing. So you and I have talked about this a bit, but it's just one of the more interesting things that I run into.
Yeah, and you know what what I love about the whole false energy, this whole discussion, is it really builds on the fundamentals of power systems engineering, because when you to really understand what you're looking at, you've got to understand some of the fundamental stuff that we learned in college.
Yeah, it's really funny. I gave you a really good example of that. I had I, I reached behind me here because I pulled out this paper, and I'll have to share this with you, Tom. And
Yeah.
this paper's online. It's basically called Power Quality Solutions and Energy Savings: What is Real? And what happened is I created that paper and I presented it at EPRI and at a couple other conferences over the years. And at one of the conferences I went to, basically I was talking to a guy that was selling these little magic boxes,
Hmm.
and it's really exactly what this paper is all about. And so I went up to him, or I kind of was trying to walk by him because I knew what he was doing, and he kind of pulled me aside and said, "Hey, buddy, come over here." He was like, "You want to see this stuff?" And I said, "I'm good," and he's like, "No, come on over." So he basically pulls me aside and he's talking to me about his little magic box. And by the way, if you paint them green, they work a lot better. So his box is green. But anyways, he said to me, he goes, "Well, have you seen our box here? It's an energy saver." And I said, "Yeah, I've seen it. In fact, that's what I'm presenting on in this thing." And he goes, "Oh," he saw my shirt. He goes, "Oh, you were for Eaton." He goes, "You guys don't like us, do you?" I was like, "No, it's not. I don't have anything against you." He goes, "Well, you guys make capacitors and yours don't save energy." And I was like, "Well, yeah, we don't claim that they save energy. We put them in for power factor correction and you get some I squared R losses and stuff out of them." He goes, "Oh, wait, so you do save a little bit of energy?" And I goes, "Well, yeah, we could save maybe, the numbers that I throw around are 1 to 4%. I said, "In fact, in my paper, you come see my presentation and all that." And he goes, "Well, I mean, I'm not saying anything much different than you. I'm just saying we're saving losses for people." But I said, "But you guys are claiming like 15 to 20% savings." And he said, "Well, yeah, but we can get there, right?" And I said, "Well, how do you get there if I'm saying 1 to 4% and you're saying 15 to 20%? He said, "Well, listen, here's how it works." He goes, "You put a motor on and let's pick a number. How much do you think you could save on one motor?" I said, "I don't know, 1 to 4%. He goes, "Let's pick a number. You pick the number." I said, "All right, 2%. And he goes, "Okay, Mr. Smart Guy." He goes, he goes, and he backed up there and he goes, "Let me ask you, in college, where'd you go to college?" Yeah, man, we learned about power systems. Tom and I learned about power systems.
Mm-hmm.
He goes, "Okay, at your college, how many classes did you have on power factor correction?" And I said, "I don't know, like a while." He goes, "Let me tell you how many you had." He said, "You had 3." He goes, "Probably like 3 days you spent on power factor correction. So you really think you learned like everything you need to know?" And he's going on and on about this. I said, "Okay, where are we going with this?" And he goes, "Again, pick a number." I said, "All right, 2%. And he goes, "So we agree that you could save 2% on a motor?" And I said, "Sure. If you have a motor that's way out at the end of the line and you put a capacitor on, you reduce the current, you reduce the I squared R losses." Okay. And I said, "But you said 15 to 20%. He goes, "Well, bear with me." He goes, you got a motor over here, you save 2%. He goes, I said, "Yeah." He goes, "You got a motor over there, you save 2%. One over there, 2%, 2%, 2%. Pretty soon you're up to 20%. And I go, "Wait a minute. Let's not stop there. How about if I put so many motors in that the utility pays me?" And he goes, "What are you talking about?" I said, "Exactly. Do you understand per unit?" And he goes, "No." He's like, "What are you talking about?" And I'm like, "If you save 2% on every motor, you still save 2%." And he just could not. And he's like, "Oh," and I literally asked him, I said, "What did you used to sell?" And he said, honestly, he used to sell cars. And I'm not cutting on people that sell cars. I'm just saying he had no idea about electrical
Yeah.
stuff. And so all the people that we deal with kind of in this space are super passionate about what they do. The point of what I try to do and what we're trying to talk about here is just kind of like making people aware of, what works and what doesn't work. So we built some demos, and I shared with you that video that we made that was actually kind of a more fun one that we made about saving energy.
Yeah, and I put the video link to that video is in the description for this. And also,
Uh,
I just shared that paper that you were talking about, the power quality solutions, energy savings, what is real. I put that in the chat box, both on all. We're on 5 platforms right now, so
oh well.
everybody should have a copy of it.
Well,
So what you have is you've got a group, some people out there who make these boxes, right? And they'll tell the customer, and to your point, it's a customer who doesn't understand, and they'll actually do demonstrations to say, look, this is going to cut your energy usage, and all you got to do is mount it on the wall, but it really doesn't do what they're claiming, although it does do something, right?
yeah, and that's the thing is there's a number of little ones that you can plug in and a variety of different things that they make claims to just put it on your system and it'll save you energy. And the reason that I wrote that paper was because, and it's called Power Quality and Energy Savings, What is Real, right? So the point of that is if let's say I want to sell you a power quality solution, let's say I want to sell you a surge protector. If
Mm-hmm.
I tell you, you put my surge protector on, if lightning strikes, you're gonna save your TV. Okay, that's like an insurance policy, and people don't like to buy insurance, right? But if I tell you that this is what they actually say in some of the surge protector things. They say every time you type on your keyboard, you create microtransients. Okay,
Oh,
and so those microtransients make the electrons in your system go all over the place. If you put our surge protector on, you make the electrons go in straight lines, and then you save energy, right? Now, how much energy do you save? 15% of your bill, and next month you'll use less power. Well, so there's going to be a customer that puts it in September, and they move to October, and they're paying less on their HVAC bill, and their power bill goes down. And then they tell their friend, "Look, I put this little box in; it was only $30. I saved $30 on my bill. So you should buy one." So this is how it
wow.
spreads. But the point of power quality is like it's hard to sell power quality solutions like surge protection, harmonic filters, even to the extent power factor correction and voltage,
Right.
anything that makes your power dirty, people say waste power. And it's you said it at the very beginning, which is it doesn't kind of follow the rules of electricity. It probably isn't exactly right. So, but it's a lot easier to sell energy savings than it is to sell insurance. And that's why this is such a big deal.
Yeah, absolutely. And Nick, we have Nikolai Tesla watching right now. I'm just saying, we got
Oh,
Nick
good.
Tesla watching, and he says Dan Carnovale, the arch enemy of unwanted harmonics.
Yeah. So there's so even harmonics. I mean, I have a little drawing tablet thing. I can draw out a couple of these things here, but I think it's let me kind of explain how they get to the point where they do that. And then I actually right behind me here I have a little demo that we can show you as well.
So
So
are you going to
yeah.
describe what's in that box and what it's
Yeah.
doing? Or how are you going to approach it? Are you going to talk about what it's doing and then describe
Well,
what's in it, or what?
I'm gonna just tell you what the typical situation is. I'm gonna draw it out as a one line,
Okay,
and then I'm gonna show you here in real life how the measurements really work out. Okay.
perfect.
So let me switch over my camera here, and I'll show you something. Um, and Tom, I have a special friend here for you, by the way, today.
Oh, you do?
Yeah, I thought maybe let me see if I can. Where is there it is. Okay. So I have a special friend for you today. You remember when we made that video a little while ago
And I
about
know
the fuse breaker and reclose and contactor?
and I know everybody on this channel, on YouTube, Facebook, LinkedIn, Twitter, everybody's watched that video. They had to watch that video when we paired off a breaker, a fuse. Look at this. Look at
So
that guy.
there's your guy. And honestly, like, I mean, really, that fuse is pretty impressive.
It's
And even though you lost, well, you sort of lost in the
We didn't
video.
lose. We
I mean,
broke
there
even.
was a tie, but honestly, like it was so the breaker and the contactor came in together, right? And you can even see how they come in
that's
together. But
that's right.
yeah, if you haven't seen that video, so Tom was the fuse, I was the breaker, and Eric was the contactor. That was a ball. So Tom, we have a claw machine now that we're gonna have people come in and they'll get to pick obviously Honestly, they probably will pick the fuse a lot because this is pretty cool. So I just wanted to show you that while we're here. Now, as far as what goes on with these false energy savers, I mentioned surge, but most of the time we're talking about a capacitor. And so if you take a typical power system and you have a source, and then you put on a motor, people always say, well, what's the power factor of the motor? Let's say it's 100 kilowatts, or let's say we'll make it easy, 500 kVA or horsepower. Okay, so horsepower equals kVA in my mind. It simplifies things for me, right? And 0.8 power factor. When we look at a motor on one line, a lot of times we say, 0.8 power factor, 0.85 power factor. That's the power factor that is for that motor when it's loaded, when it's doing work. And that's the one thing that most people that see this demo that they show in their little suitcase don't get to understand, because when you draw the power triangle for that, you have, 400, this is why you use 500 horsepower motor, 3, 4, 5 triangle, right? 300, 400, 500 kVA, 400 kilowatts. And one of the things I learned about kVAR, Tom, in the IEEE standard, small k, small v, a, r.
I do that wrong every time. I always capitalize K.
Yeah, so anyway, it's a small k, but anyway, 3, 4, 5 triangle, 400 kilowatts, 300 kVAR, 500 kVA, because it's 0.8 power factor. Now, if I wanted to show you how a capacitor works, I could put a capacitor on here, and let's say it was 300, make it easy, 300 kVAR, right? Then the equal and opposite shows up here, and my power triangle is not a power triangle anymore, it's just a flat line, and it's 400 kilowatts and 400 kVA and 0 kVAR. So the cool thing about power factor correction is you can do all that stuff, and it's something that people can understand when you do the math. And we'll come back to an actual example of that. But what I'm going to tell you is they don't do that. They take a motor, okay, and they hang it off of a 120 volt outlet or whatever. They connect it to the system. They don't have a load on that shaft. They don't have anything in particular on the motor, so it's just freewheeling. Now, you know what the power factor is for an unloaded motor? If I were to draw the power factor.
Oh, for an unloaded motor, it's probably heavily reactive, right?
Yeah, it's mostly reactive. So what happens is that motor only has a little bit, I'm even exaggerating a little bit here. It only has a little bit of kilowatts. And the only reason it has kilowatts at all on an unloaded motor is it has to spin the shaft. So it has to overcome friction, which is very, very little. But it needs cable. It needs reactive power to run the motor. Why does it need that? Because it has to magnetize the motor. So this is where it goes back to the rules of electricity. And so I hand a guy that used to sell cars a motor and tell him to turn it on, and he sees the motor spinning and he thinks, oh, there you go, the motor's spinning and it's using watts. Well, it's not really using a lot of watts, it's only just overcoming friction, but it's using a lot of VARs, a lot of reactive power to make the motor spin. So what's the power factor for that? Power factor for an unloaded motor is about 0.1, okay? And that's super important when you start to look at what they do to fool people into thinking that they're saving energy. So now, if I put a capacitor on, and I hang a capacitor right here, right? So I stick a capacitor on and turn it on. What have I done? Initially I have watts and VARs coming that way, right?
Mm-hmm.
Now I have VARs that are kind of equal and opposite of the motor. So if I put a capacitor on that's equal and opposite of the motor, look at my resulting power triangle. Still has a little bit of kilowatts, but maybe the kVAR is like this. So maybe I've negated, 2/3 of the kVAR.
Okay. So what you're doing then is your VARs is subtracting from the VARs from
right.
that the motor's putting in.
This is minus kVAR, and this is plus kVAR.
Okay.
And And so what happens is your kilowatts don't change because you're still trying to overcome the friction of the motor. Okay.
Hmm.
But what happens is your bars change, bars, right? Big bar. Um, and what also changes is your kVA, the hypotenuse of the triangle. Okay.
Yep.
So you know what they do though, is they don't say, here's your old watts and here's your new watts. You know what they show you? What do you think they show you?
The
They
kilovars.
actually they actually show you amps.
Oh.
Actually show you amps. Okay. Now, when somebody that's unfamiliar with electricity says volts times amps equals what, most people will say watts. But we know in AC power systems, volts times amps equals volt amps. Okay, so this is kVA or volt amps, right? And this is
Hmm.
kVA or volt amps. How do I get kVA? I multiply the voltage times the current. Get kVA here, voltage times the current. So what has really changed here to here? Not my watts, but my kVA and my kVAR. So if I show you amps, amps are proportional to kVA. So if I told you I had 100 amps here and 50 amps here, I could be totally truthful to you, right?
Yep.
But I would also, if I didn't know better, I might tell you that I'm saving 50% of my power.
Uh,
Okay. And that's where they fool people because guess what? Do we pay for kVA? No, especially not in our house.
nope.
We pay for watts or kilowatts, and we pay for kilowatt hours. In a
Right.
commercial building or even an industrial plant, most of the time we pay for kilowatt hours and we also pay for kilowatt demand. Okay. So in that case, we pay for kilowatts in both cases. Um, you know, there are special exceptions where the utility will bill you a power factor penalty, but that's saving money, and we can come back to that. That's not saving power as we define it as kilowatts. And so if I look at my, again, if I put my magic box on there and I don't tell you what's inside and it's just a capacitor, and then I put it on and all of a sudden your amps go from 100 amps to 50 amps, you're going to be pretty excited about it if you don't know the background of what's going on, right? So there's, in fact, I'll tell you a little secret that one of our plants, not in the electrical group within Eaton, but another group within Eaton, bought like 3 of these years ago. I got involved in a project, and they were like, how they wanted to explain to me something. I can't remember exactly how I got involved in the project, but they wanted to explain to me how they were saving energy. And basically they put in, here's their system, utility storage transformer. They put in 3 of these magic boxes, right? 1, 2, 3, and they had their loads down here. And so looking at their bill from last year to this year, as an example, when they were doing the project, these magic boxes were saving them 15% of their bill. And I was like, what are they? And they said, well, they're just these energy savers. And I said, well, I think they're capacitors. And I went out and did some measurements and I proved that they were capacitors. But you know what else I found out, Tom, was funny? 2 of them had failed. Okay, so 2 of them blew up because of harmonic resonance. They only had 1 running, and they still thought they were saving energy. And you know why these things work? It's because people really want to believe they work. So the plant was convinced that putting these magic boxes in there saved them energy. And so looking at their bill from last year and comparing it to this year, they saw that their power in April last year and this year was different, and in May and so forth. And I said to him, I said, well, when did you put the boxes in? And they said, well, we put them in June. And I said, well, how were you saving energy back in April, May?
Yeah.
Well,
Yeah.
that was just, and I said, well, what else did you change in the plant? And they said, nothing, and I said to them, I'm like, well, something changed. And they said, well, no, nothing changed. There's nothing else that really changed. I don't, I'm not sure what you're asking about. And I said, well, tell me how does, I said, do you use more load or less load? And they said, no, in fact, the only thing that changed was we changed our lights. we went from like normal lights to fluorescent or whatever. And so obviously that was their energy savings, but they had attributed
Right.
this whole idea to these magic boxes.
Well, so basically what I'm hearing an echo. Do you have the other one on too or something? No. Okay. All right. So basically what you're dealing with is power factor correction, which changes the VARs. It'll lower your VARs, but your watts stays the same. And we get billed on watts. Now, Santiago brings up that he says, but it could be presented as a benefit if the user is being penalized for poor power quality. And I wouldn't say poor power quality. I would say if they're being penalized for power factor.
Correct.
Right?
Yeah. And that's exactly right. So let's go back to that example. I'll make up an example here and show you one. So if we look at the power system, here's our transformer utility company. And we have a load and we have a bunch of motors, and our load is, let's say, a poor power factor. Let's say it's 1,000 kVA at 0.7 power factor. Okay, so we have a significant. Let's say this is 1,000 kVA transformer. Well, I can only supply this load at 1,000 kVA at 0.7 power factor. If I wanted to put another load on here, let's say I wanted to put another 100 kilowatts or kVA, let's say 100 kVA, I can't do it because I'm going to overload that transformer.
Right.
So the utility says, okay, if you put a capacitor and you size that capacitor to compensate for that low power factor, theoretically, right? What's the power factor equals kilowatts over kVA simply, right? So then your kilowatt equal 700 because power factor times kVA equals kilowatts. So if your kilowatts is 700, you're really only paying them for 700 kilowatts,
right?
But you're using a capacity of 1,000 kVA. So they say, so you call them up and you say, hey, give me a 1,500 kVA transformer, and you know what they're going to say? No. How about you put capacitors in there, or we're going to bill you, $2,000 a month until you fix your power factor, because you're using capacity of my wires. And again, what are wires rated in? Amps. What are amps proportional to? kVA. They're not proportional to watts either. So all my devices are either rated in kVA or amps. So the utility wants me to fix that, and that's so he's exactly right that we would potentially get power factor penalty. And if you save $2,000 a month, you can save a lot of money. But what you're not saving is actual watts.
Right.
With a little bit of an exception of if you had, let's again say a motor way down here, and I reduce by hanging a capacitor down here, I reduce my current here, then my I squared R losses along that line, I could basically save that. So that is exactly right.
Yeah. So kVA is that hypotenuse of the triangle. So whenever you if you're horizontal, that's your kilowatts, that's your VARs, and there's your kVA. So if I reduce the VARs, my kVA is lower because the angle is smaller.
Right.
Right. So by reducing the kilovars, my kVA comes down, which means the amps is coming down because, like you said, kVA is proportional to amps, or amps is proportional to kVA. And so my amps will come down. But to your point, if I put that down at the motor, I can reduce my losses. But then, that's not a lot of losses. I mean, you got to think about it.
Right. I've done a lot of I've done a lot of analysis in that area, and we actually kind of did like a high-rise building in I guess it was Canada. See a little bug crawling around there? That's pretty cool. So anyway, it was a high-rise building, and they were using around 1,500 kilowatts of load, and by doing power factor correction, even out at the very end of the HVAC units and all the motors and stuff like that, if we exaggerated it, we could probably get around 2%, maybe 3% savings at the very most, right? And that's really just because those I squared R losses, the resistance of those lines, even at the, even if it's 400 feet away, it's just not that much. You know where most of your impedance is? When we do fault studies, where do we count? We don't really even hardly pay attention to those lines. We pretty much look at the impedance of the transformer.
Yeah.
And the X over R ratio for a transformer is usually what, 10 to 1 or something like that. So it's, it's a very highly inductive system, and the resistance of it is not, it's pretty small. So again, since that's not a lot of resistance here, and there's not a lot of resistance down here, the chance of saving real watts is not significant.
Right. Now, Santiago has a question. He says, what would be better for power factor improvement? A capacitor at each user, or a compensation system from the network operator considering resonance? And he says, considering resonance.
Well, that's the thing you have to worry about today is resonance. So I would argue that, I mean, he brings up a great point. If you think about resonance, we think about like putting a capacitor at multiple locations or any location really in a power system, and if the interference or the harmonics that come from the load interact with that capacitor in parallel with the service transformer, you could have parallel resonance. So generally speaking, when harmonics are involved, I try to keep the capacitor centralized. I try to keep them together on a main service. It'd be great if the utilities will do it for you, put it on their side of the system, but most of the time they want you to do it on the downstream side of the transformer so you can save that capacity of the transformer. Because it goes back to that, the beer analogy, right? I mean, we talk about that all the time with power factor correction and filling up the glass, So a compensation system today, whether it's capacitive or active, has to account for harmonics. And so an active harmonic filter, for example, could work really well, but it's probably a lot more expensive than either a fixed filter or definitely like a capacitor, straight up capacitor. So when I put on, for example, I'll show you. If I put on again, I have my source and my transfer, and if I put on a capacitor there, that's a 60 hertz compensation for all my other loads. If I put an inductor in front of that, the tuning point of that may be fifth harmonic or whatever frequency I'm trying to roll out, but at 60 hertz, it mostly looks like a capacitor. So what you would have to do if you knew you had variable frequency drives and other stuff here, you would make this into a harmonic filter so that you don't interact, from a harmonic standpoint. That's a whole other discussion. We talk about resonance and everything there, but
that sounds like a good idea for another program.
Yeah. Do you want me to maybe shoot over to the camera and show you the demo that I have here set up?
Let's do a demo.
Okay, so what I'll do is I'll turn on that camera and I think it'll pick up.
While he's doing that, so he's going to set up a demo, and I think it's going to have a motor, so he's going to do a video of a board, and we'll see how this comes through. I can see your chin now. Nobody else can see your chin. Okay, there we go. All right, there we go. Here we go. So why don't you describe what you got going on here?
Okay, I'm going to turn this microphone on. Tell me if you can hear me. Can you hear me there?
It's echo. I got an echo.
I had to kill my camera, my one over here. All right. Now, can you hear me okay?
Yeah, I can hear you good.
All right.
Still hearing an echo though.
Okay. I'm gonna leave my speaker off, and I'm just gonna show you what's going on. So you can hear me okay, Tom?
Yeah, it sounds. I can hear something in the back. I can hear like not an echo, but it's like a double voice. Not sure why.
All right. Let me try this.
This is what's great about being live. Ooh, now that's a big echo. Ooh.
All right.
We'll get this straight. This is what we do. Living on the edge.
Is that better?
Yeah, that's much better.
Okay. All right. Sorry about that. All right. So what we have here is basically we have our motor, and if you notice what's connected to the shaft there, nothing. So it's an unloaded motor, right?
Yeah.
And normally that would be connected to a gear or maybe, like a, who knows what, like, basically a belt or something. And but basically that motor is going to be unloaded. So what's going to be the power factor? Like 0.1. It just needs to overcome friction with not a lot of effort. It's not going to be a lot of watts. So again, work equals watts, and that's the important thing. So as I turn on, so I have a switch over here that turns on the motor and turns on the capacitor, and I have a little meter that's going to show us the amps and the power that we're using, so forth. So I'm going to turn on the motor, and now the motor's spinning. So I don't want to touch the motor shaft there, but basically the motor's spinning. So now if I go up here and I look at my amps, can you see that, Tom?
Yeah, I can see it. 6.08 amps.
Okay. Now, here's my magic box, and I'm going to show you something. They charge about $600 for some of these, and you can see what's inside there. There's really nothing but capacitors in there. So when people say, "Oh, the Eaton ones are different and whatever," I mean, these capacitors are capacitors. They're very similar, right?
Yep.
So turn that on. You're going to see the light go on there. Okay. And now let's go back over here to our amps. And now what are we reading? We're reading amps, 3 amps.
Yeah.
So I just saved you 50% of your power, Tom. Can you believe that?
I'm buying it. Wait,
Yeah.
where's my let me get my here. Hold on. I got my
you
wallet.
only have to buy 2 of these to get more than 100%. So, you're going to get over 100% savings if you buy just 2 of these units. And that's what I'm here to sell you today. I'm going to go back in the back room and talk to my boss. And if you want 2 of them, I'll sell them to you today. But you got to make a decision right now, right?
All right. Well, I've got some cash on me.
Yeah. So what else I can show you here, though, which is really funny, is that this meter that they always use to prove the savings.
Yep.
Also measures. Break this back to normal here. Also, you lost me there. Right?
I got you.
Also measures watt. And so that's what you say, 165 watts.
165 watts. Okay.
So my capacitor's on. Both of my switches are on. Okay.
Yep.
I'm going to have you watch the watts at 164, and I'm going to turn off the capacitor, 165. All right. Just to prove to you, see the light on the capacitor is still lit, but it's getting dim because that's what capacitors do, but the switch is off. It's bleeding off, whatever, but it really hasn't changed at all. In fact, with the capacitor off now, we have a little bit less watts. So the watts haven't changed at all, which is exactly what we said it would happen, right? The other thing that's interesting, so that's, so there's frequency, here's VA, okay? And we talked about VA. And
that's your hypotenuse.
Yeah, so it's 7.14. I'm going to turn the capacitor back on. And guess what? It goes to about half, 3.5, 3.6. So that's it's not a surprise at all, really. There's our watts.
Watts is always staying the same. You're changing the VARs, and that's why the kVA is getting lower.
Right, and the voltage is, of course, staying the same, so they're not going to make any claims about that. But the power factor, again, this measures power factor with a capacitor on.
It'll take it down to 0.1 or close to 0.23.
Yeah, so this one happens to be a little bit different, but 0.2, 0.1. But and again, what's interesting is there's no claims about sizing these exactly for the load that you have either. They just take one size fits all, put it in your house, and you'll be good. So that's what's, to me, that's what's funny too. Is it's just too good to be true. And you remember what they tell you about too good to be true?
It's definitely too good to be true. So, and what's really interesting about this, Dan, is you're simply working off of that power triangle, right?
Yeah, right.
So you're changing the VARs, and we're watching physically the VA going down. The watts is always staying the same. So if you get, well, we all get billed for watts because that, like to your point, that's what does the work. You said it. Work equals watts. So
Right.
if you're getting billed for watts and you put the power factor these capacitors in, you're going to change the VA, you're going to change the
Yeah.
VARs, but if you don't get billed for a power factor correction penalty, your bill will not change.
Exactly right. And that's the biggest and the most difficult thing to explain to people, Tom, honestly. Like
Yeah.
it's very frustrating because, like I feel bad because there's a lot of people that are buying into these concepts and really don't know better either. And that's the problem, is they kind of have decided that this is going to work, and they want to prove it because they've spent some money on it, right? So what happens? It's a placebo effect. If you really believe that you're saving money, you'll turn off the lights and yell at your kids to close the doors, and turn off the air conditioner and stuff, or whatever, or turn down the air conditioner. But the reality of it is you're not saving watts.
Right.
It is just so let me show you one other thing that they do, because a lot of times in these magic boxes, they will show you um, they will show you a little bit of savings um, on the watts. And here's how they do that. Try to adjust my camera here a little bit. So here's 50 feet of lamp cord. Now, why lamp cord? Because it's 18 gauge, has a lot of resistance.
Yeah.
Here's another 50 feet of lamp cord. Okay.
Yep.
So right now we're at kilowatts or watts of 160. Okay. And my capacitor's off. And now my capacitor is on. Okay. There it is. It's on. Now watch what happens down here at the motor. Okay. I have 159 watts. Up there I have 161. I have a little bit of losses in my line, right? Very
Right.
But if I put on this 50 feet of lamp cord here, okay, then I go back here and I put on another 50 feet of lamp cord. What do I see? That hasn't changed that much. But down at my motor, now I've changed my losses along the way because I'm feeding that same current roughly through a much higher resistance. But trust me, 500 MTM and bigger conductors that are going out and feeding the loads that we see out on the
Right.
systems are not going to do that. They're just not.
Exactly.
They're not that same I squared R loss.
Yep. And what they'll do is they'll do a demonstration for, say, a homeowner or somebody who
Right.
builds homes, and then and those individuals think that, hey, I can advertise this, or I'm going to save money, and they buy it, put it on their house. And to your point, if they are watching their energy bills go down, it's not because of this, it's because of other things they're doing, because they're more energy conscious. So like you say, it's a placebo. But I tell you what, if I put this on my house and I truly thought it was giving me free energy, I would tell everybody in my house, turn on every freaking light you can.
Oh, for sure. For sure.
Because it's free, right?
Free energy. It's free energy. I'm going to switch back to the other camera here. Hopefully I won't lose you on there.
All right. Okay, there you go. You're back to the drawing now, right? Back to the drawing board, ladies and gentlemen. And we got Felix
Okay.
in the house. Mike Solo. Mike Solo says, I wonder what a typical suburban home's power factor is. Other than HVAC, doesn't have many inductive loads in the house. Now, here's the other thing, and what I learned, Dan, and Mike. So, we typically will associate with lighting and whatnot a unity power factor because of incandescent bulbs, but LED lights and compact fluorescence and fluorescent lighting has a very, especially your compact fluorescence and fluorescence have a very bad power factor. They could be down as low as 0.5. So from a residential perspective, your power factor could be pretty bad. That angle could be large because of those other types of loads outside of HVAC. Just your lighting.
I'm glad you brought that up. That brings up a great point. Okay, so what is power factor? Power factor equals kilowatts divided by kVA. Okay,
Hmm.
and we know that this is kilowatts, and this is kVAR, and this is kVA. Okay, now in terms of linear load, 60 hertz load, that's exactly what you have. In terms of harmonics, guess where harmonics are? They're not kilowatts, they're not kVAR, but they're in this axis. So think about a three-dimensional graphic, three-dimensional plot, right? So if I do this, now if I could draw in 3 dimensions, I'd be much better. I'm not that good at it.
You'll
So
never be an artist.
I'll never be an artist, but the reality of it is this kVA, which is the 60 hertz part, is kilowatts over kVA here, 60 hertz voltage and 60 hertz current. This kVA includes harmonics. So guess what? The more harmonics you have, the bigger your kVA is, which does exactly what you just said. Your kilowatts didn't change, right? Because harmonics aren't affecting the kilowatts. But if your kVA is bigger, what does that make your power factor? Makes your power factor smaller. So the more harmonics you have, the worse your power factor will be in terms of what they call total power factor, TPF. Okay. What utilities bill for on commercial industrial systems is called DPF, displacement power factor, and that's just 60 hertz. Okay, you know why? You came out of the metering group, Tom, so you probably remember when the digital meters came out, and all of a sudden you can measure all kinds of crazy stuff, and people got excited about it. So you could measure this
Yeah.
power factor, or you can measure that power factor. Well, the old meters used to just measure this one. And so let's picture you being in an industrial plant that uses 3 megawatts, right?
Hmm.
And you don't have a power factor penalty. And then I come in and I put in a new meter, and because you have harmonics, because you have a bunch of drives, now I have a power factor penalty.
Oh,
And I didn't
yeah.
have one yesterday. So they screamed about it, and basically what happened was the utility said, fine, we'll just bill you on displacement, 60 hertz.
Absolutely.
Nice. That's good.
There we go. It's that's your
Magic
magic
bean.
beans.
So I think, when you think about like what happens in that case is, let's say somebody's selling a harmonic filter. If they're selling a harmonic filter and they're correcting this, are they correcting this? Not really.
No.
Not any more than they would from the I squared R law.
Right.
So it tends to be sort of this, like you said, you'd be so excited about it that maybe then you might want to do it. The other thing that's kind of interesting, and people, I sent you that PowerPoint. I don't know if you have
Oh,
a chance to pull it
yeah.
up, but
Let me call it up. Hold on.
yeah, but EPRI says something that's, to me, interesting. And if you look on, I think it's on slide 15 on that PowerPoint presentation.
Hold on. It's coming up now. I got to. I didn't have my email open, so.
So basically, they say you can only save energy that's wasted in terms of watts, right? So if we call energy kilowatt hours, we can only save kilowatt hours that are wasted. So by putting in a capacitor, I'm not really adding. It's not a power generation source. I'm adding in reactive power that happens to be equal and opposite of the magnetic forces it takes to spin a motor. So you never get there with kilowatt hour, with capacitors in terms of all that extra energy. So yeah, so they use it, and then I had a couple slides, like the next slide, for example, shows a little bit of the calculations that go into it. And so, you say, well, I could save 8.1% of my 8.1% of my whatever kilowatts over the whole thing, right?
Right.
But that's if you put a capacitor way down at the end. But look at where that savings is coming from in terms of losses, right? But the actual savings, the difference is 11 kilowatts if you put a capacitor on. So if you go to the next slide, on slide 17, that it shows 11. So it's, 15% of the losses, but it's really only like 1% of your bill. So that's the key thing, right? And so numbers get thrown around, and things get a little confusing. And then the next graph is the one that I did for that high-rise building, where we did an actual calculation. And oh, by the way, if you put in a capacitor that's too big, guess what's going to happen? You're going to draw too much current,
Oh yeah,
and I squared R losses go the other way. So
that's right.
that's,
Yeah,
you
you're
know what I
over.
mean?
You're
So
overcorrecting.
exactly. So yeah, it's just one of those things. I'm very kind of passionate. You talk about passion. I'm very passionate about telling people what's real and what's not. And so when you think about, like, people get mad at me, like I let them come in and they tell me their little story about how their device works differently. And in that PowerPoint, I'll point you to a couple other things that I think are kind of interesting. Let's see. There's some quotes at the very end. Oh, go to yeah, I didn't even yeah, let me see. Quotes towards the end that are confusion created by sales, right? So if you go to slide 35, Tom.
35.
Yeah. What they'll try to do is they'll try to find who they believe to be a technical person for the facility, right? So they go, well, let's have the technical guy watch, or guy or lady watch this, this little presentation I have in my little suitcase demo. And let's have them understand. So before I put my capacitor on, you have this many amps, and now you have this many amps. So you understand that, right? And you're biomedical engineer, so you're pretty smart, right? Well, they're not necessarily electrical. They happen to be in this job and whatever, and they didn't have that electrical background, but they're trying not to act, right? So they're pushing this.
Right.
And then once they do that, you know what they do next? They go to the CFO or somebody and say, look, this person believes this. I just showed them I could save you 50% of your power. And I'm not even claiming that. I'm just going to save 15%. So if you're more than that, that's all money in your pocket, right? So they go through these things. They get this technical sign off. And I've seen that many, many times. The other thing is they always claim this patented technology. Well, it's either a surge protector, or a capacitor, or a harmonic filter. That there's no secrets here. So it's all about the basic stuff.
Well, it's
They
secret.
patented,
It's all secret until you open it up, right?
yeah. Well, they usually put epoxy in there. It makes it heavier and weighs more, so you get more price per pound,
Okay.
and stuff like that. So you can't see what's in the box, but trust me, they're capacitors. And then my favorite one, and I've heard this probably more than 100 times, only the inventor truly understands the technology. So when you hear that, that should be like a huge siren and red flag and stuff like that. And it's kind of funny because, like, so if Kirchhoff came back, or Ohm came back, or like Tesla or Westinghouse, or one of those guys that understands electricity, like, they probably wouldn't understand it because they're not the inventor, and it doesn't follow their rules. It only follows these new rules. So that, again, big red flag,
Yep.
huge red flag. The other thing on here is it's really hard to prove and disprove guarantees. So if I sell you this box, if I sell you one, guess what I can do? I can measure just like I did there,
Yep.
turn it off, turn it on, improve the savings. You know what they want to do? They want to sell you 25 of them. Because if you put them all around your facility,
Oh.
and then you can't really easily turn them all on and off, it's hard to prove that or disprove that it doesn't work. But they basically rely on the fact that you're not going to understand the difference between current and watts, because in grade school you learn that volts times amps equals watts. And until our teachers understand that, and they tell us, hey, that's only for the DC world.
Yeah.
But I think you should go around and do a program with all the teachers in grade school, Tom, and tell them that volts times amps doesn't equal watts.
Oh my gosh, that would be awesome. You know what I could do? We could do an Abbott and Costello skit.
There
You know?
you go.
You're
Yeah.
like, who's on first? What's on second? Third base. I love it.
I know. But anyway, see what I'm up against when I kind of do this, and it's just.
And it is. I mean, it's like you said, it's like talking to somebody who knows how to dance around the technical issue. They'll make relations that sounds valid, but in reality, it's that third dimension. It's the it's the fact that that works in a DC world, but it doesn't work in an AC world because you've got the magnetics and the magnetism and the VARs aspect of
Yep.
things, and that distorts the VA, and it's easy for somebody who's not on their A game or even their B game to
Yeah.
get deceived by something like that.
Now, let's say I come into your plant and I sold you this, right?
Yeah.
Go to slide 24 once. I want to show you something. So slide 24 is the one that happened at the Eaton plant because I actually had that data. So let's say I come in and I sold you this idea and you didn't really understand that it didn't work. And you really promoted it up through your CFO or whoever, your boss,
Right.
Are you going to go back to your boss once you find out the truth?
Oh, that's
No
like,
way,
there's
right?
no way.
No way. So you're going to pretend it never happened. You're
That's
going to hope
right.
for you're going to hope for like some interesting weather pattern to change so that they use less air conditioning or something.
That's
Um,
right.
but reality of it is you're never going to bring it up again. And so the bad part of that is I actually had a person one time call me and they read my paper and they said, hey, I was in the military. I got an honorable discharge. I had a little bit of money saved, and I bought into this company that sells
Oh,
these boxes. And he goes, are you telling me that they don't really work? And I said, I'm not telling you they don't work. I'm telling you they don't save energy. And he said, oh my God. He goes, I've been told a story and I felt horrible for this person because here's this person that invested all this money. It's this pyramid scheme, and all this stuff. And I felt really bad. And so my point of doing a lot of this is really just to let people know what's going on in the
yeah.
world.
Awareness, and that's the whole thing on what I do, what you do at the Experience Center, what we do as
Yeah.
Eaton, and others like Nick Tesla and Brian and all these guys. Basically, we try to educate and teach people because the more educated we are as both engineers, contractors, as consumers, the
Yeah.
better choices that we make and decisions. Because I mean, we're in a world of cybersecurity issues, and the worst thing is when you fall for something like this and
Yeah.
say, I should have known better,
Yeah.
and to your point, and so here's the other thing that happens. You get a person who buys this technology, okay, buys in on this, gets it into the facility, starts to show the energy savings because they're doing other things, to your point. And then what happens? They get promoted, okay?
Yeah.
And
Yeah.
then a guy like me comes into that role, and all of a sudden the energy usage starts going up, and they say, what are you doing?
Your fault.
He bought this equipment that's supposed to save energy, and the only thing that's changed is you.
Right. That's a good one, actually. That probably happens a lot more than
Oh,
you think.
absolutely. That's exactly the way it goes.
Yeah, and the funny thing is on if you go to slide 37, well, again, one of my favorite quotes is it just, I know you don't understand, but it just works, it just does. But they always say you can't install one, and then they say these things like these capacitors are different. Now, on the plant where I told you that at our plant we had 3 of these units, and 2 of them failed because of harmonic resonance. Again,
Oh,
you can't
wow.
just throw a capacitor on and expect it to live through resonance if you have a bunch of harmonic loads. But anyway, 2 of the 3 failed, and they still work, even though they were failed. Um, so that's real true belief there when they're not even online and they're working.
They're still
But
working.
but but the thing is, they were like, these are different capacitors. You know what? So I opened up the box, I drilled out the rivets because they always rivet them shut because they really don't want you to look at them. I opened them up. It looked like somebody took a broom handle, coiled a piece of wire around it, like a 10-gauge wire, and that was their harmonic filter. It was an air core filter.
Really?
Yeah, but guess whose capacitors they were? They were our capacitors, Eaton capacitors, right? So again, I kind of basically kept saying they're not different than regular capacitors, and we even proved the point that we bought
Yeah.
these capacitors through another vendor that was, there's no difference. It's just the
Okay.
rules of electricity work.
Yeah. Now, Santiago brought a good point, which, okay, in my little advertisements for this whole session, I think, in my opinion, Dan, there is not only is there a lesson to be learned to not fall for this, but the fundamental principles that we're talking about this whole concept of power factor correction and amps, we can leverage this in other areas in the power distribution system. And Santiago points out, he says, can you reduce the ampacity of the conductor and the capacity of the overcurrent protected device, reducing the current with a capacitor, or is it not beneficial enough? So I've seen this done where if you have a transformer, right, and you say, and I think you brought up the case where you have a transformer and it's a certain kVA rating. If I have to put more load, I could put a power factor correction capacitor on the secondary to reduce my kVA.
Right.
But I'm not changing the watts, but I'm reducing the kVA, and now my transformer can still supply that, and I could pull less amps for downstream using less of the percentage of my my conductors and whatnot.
Yeah, I actually worked out a problem here for that power and focus event that we're doing next week. We're doing a hand calculation section on that power and focus event on the 23rd, and I go through like transformer calculations for full load amps and fault current and stuff. But one of the things I did is power factor correction. So I'll show you the example I did for that, because it hopefully it'll kind of explain a little bit more of what's going on here. So let me zoom this out.
Oh, nice.
But yeah, so here's your transformer, 500 kVA. You'd have 400 kilowatts. We showed that earlier, 300 kVAR. So your 3, 4, 5 triangle. Your initial power factor would be 0.8. So it would be, 400 over 500. That's your power factor. Okay.
Right.
So let's say you wanted to put a capacitor in, and your target power factor was 0.95. So what you would do is you'd say your kVA new, my new kVA here, okay? My new kVA would be 400 over 0.95 or 421 kVA. So I can calculate my kVAR, 421 squared minus 400 squared. It's just a right triangle. So I get 131 kVAR. Now, with 131 kVAR, that's not the size of the capacitor. That's what's now flowing down through my system. So what you have to think about for power factor correction is, how big is the capacitor that would give me 131 kVAR? And the answer is 169 kVAR, which is not a standard capacitor. So I in my example, I said, well, you'd pick either 150 or maybe a 200 kVAR, which might be a standard capacitor. If my target power factor is 0.95, I'm not going to pick a smaller capacitor and give me less kVAR. I'm going to pick a bigger capacitor. So I put a 200 kVAR capacitor there. If I had 300 and I put 200 in, I'm left with 100. So my new kVA is 400 squared plus 100 squared, 412 kVA.
Yep.
My new power factor, 400 over 412 or 0.97. So my target, my utility is billing me for 9.5. I'm getting 0.97, so that's good. And my new power that's running through my system here is 400 and 100 kVAR. And so I have a total going through my transformer of not 500 kVA now, but 412 kVA. And so that leaves me with capability of adding more load, or as you said, at some point you could even reduce the size of that transformer if you got down small enough. For example, you wouldn't typically take a transformer out and put a smaller one in, but the point is, you wouldn't have to put a bigger one in to add more load.
Right.
And as far as the protective devices downstream and stuff like that, a lot of times, obviously when you build a system, the cables and the breakers and everything are set up for that size. So, again, you could relieve some of the capacity, but that's kind of the point.
Yeah, and you still have to protect the conductor at its ampacity, so you're not going to change that out. But like you said, I can put additional load on that transformer, maintaining the a lower kVA based on my usage. Now, the other question that came up from Felix was, what about the interaction between a capacitor and variable frequency drives? Now, you had talked about that a little bit earlier, but
I can draw that out pretty quickly. It's actually a pretty, I want to say, straightforward. It's not overly complicated, but if I can remember the numbers I used here. Let's put a drive here in front of a motor, right? So what's VFD going to do? It's going to produce harmonics, and we say that harmonics flow out of the load into the system. So they flow up here, and where do currents want to flow? Current wants to flow the path of least impedance, right? So we go, there's no other path, so it's going to go out. And people think harmonics flow to ground. They don't. They flow out on A, back on B and C, out on B, back on C and A, and so forth. But if I put a capacitor here, what have I done? I give this current another path to go into. And if I look at a graphic of sort of impedance, if I'm looking into this bus, with my little eyeball,
Right.
looking at this bus, I could have a low point for that impedance. If this is impedance and this is frequency, at some frequency, it's going to look like a sink. It's going to look like a harmonic filter, essentially. But the problem is it's also going to look like a high impedance here. And that's because this capacitor and this inductor, which is a transformer, are essentially in parallel. So if I have my harmonic current source, I put out, and I have an inductor here, which is the transformer, and I have a capacitor, okay?
Yep.
And I have, remember, XL is 2 pi FL, right? And XC
1 over.
is 1 over 2 pi FC, and there's a J in there, right? So what happens is this and this one, let's say this is 10 ohms, J 10 ohms. This is minus J 10 ohms at some frequency, right? So
Right.
what happens if you put a parallel combination of that? It's X1 times X2 over X1 plus X2. So now I have X parallel equals some number over top of what? 10 minus 10 or 0. And that becomes
infinity.
Basically infinity. Now we know it's not going to be infinity. There's some resistance in here and whatever. But either way, let's say this is 1,000 ohms. Okay. So I put out 10 amps of harmonic current. 10 amps here. What's going to happen in this circuit that we call the tank circuit, the resonance circuit between these two? It's some frequency. I'm going to hit resonance, and this current is going to flow in this loop. And let's say it's 1,000 ohms. Well, if it's 1,000 ohms, that means I've got 10 amps times 1,000 ohms equals 10,000 volts. It's not going to get there. Something's going to fail before it gets there. But let's say it got up to some number, so 10,000. And then what would the current for each component be? It would be, so if the voltage equals 10,000 volts and the impedance is 10 ohms, then my current is 1,000 amps, right? And so that's what the problem is you're going to have current flowing through an inductor, which is the transformer, and through the capacitor, which is your power factor correction. And one of those two is going to fail, hopefully, because it's a self-correcting problem, we'll call it.
Yeah.
Something's going to blow up, right?
Yep.
And if this one blows up or blows fuses, then at least it takes it out of resonance. You don't have that issue anymore. Harmonics go back to the source. But anyway, so that's a great question, and it really does that way. Now, the easy calculation for that is, say you have a 1,500 kVA transformer, 5% impedance. Then you have a load here that's a drive, and you know which harmonics it's going to produce. If it's 6 pulse, it's NP plus or minus 1. Again, we should probably do something else on this, 1.5, 7, 11, 13, etc. If I have that's my harmonic source, so I know I'm going to produce fifth harmonic, 7th, 11th, 13th. If I put a 600 kVAR capacitor on, almost put a capital A there, Tom.
I saw that. I was going to say.
So my resonance point, my frequency of resonance, is the square root of the short circuit kVA over kVAR. Okay. And my short circuit kVA, just like we do for fault calculations, is 1,500 over 0.05, which is 30,000. Okay. So 30,000 divided by 600. So if I cross that off, I get 50. I take the square root of 50. That turns out to be what, 7.1 or something like that?
Yeah.
Can you tell I've done this calculation a couple of times?
I could tell.
So, so this seventh harmonic that's produced by my drive is going to get amplified. And what you're going to see in this circuit here between these two is you're going to see your 60 hertz current, sort of, but then you're going to see this seventh harmonic current superimposed over top of it. This really big seventh harmonic current. And that's going to either, again, blow up the capacitor, blow the fuses, or hopefully it doesn't, but it could also fail your transfer.
Yeah. And so to avoid something like this calculation is what you would want to do. Once you start adding capacitors, and if you have drives, you would do what? A power quality analysis, right?
Yeah, so most of the time when you put capacitors in today, you have to assume you have a harmonic source. And you mentioned LED lights. That's a big one. Drives, rectifiers, car chargers, stuff like that. So when that happens, what you typically would do is you would want to make this into a harmonic filter. And again, by doing that, what you end up with is, remember how so a harmonic filter has a parallel resonant point and a series resonant point. If you put the series resonant point at the lowest harmonic that you would expect, the fifth harmonic, then look where your parallel resonant point is. It's below any harmonics that you'll ever see.
Right.
So you never have to worry about it. And that's a simple kind of oversimplification of how you design filters. But you can make that capacitor into that. And remember what I said is, if it's a harmonic filter at 60 hertz, it still looks like a capacitor. It still does its power factor job.
Right.
But you don't have to worry about that.
Yeah. So you would, that's called tuning the system, right?
Tuning the filter, yeah.
Yeah. So you're basically setting that point for the lowest harmonic that you'll see. So your series resonance is much lower, and you're never going to see it. And then that's basically an analysis that somebody will have to do. So, and right. Unfortunately, I mean, just placing power factor correction caps or whatnot in a system is not that simple. You should do this analysis.
And that going back to the false energy savings things, again, since we have the power quality lab here and we do a lot of that testing here, frankly, like what's happened in the past is when people bring in these magic boxes, I'll set them up with this, with the lab in there, and we'll set up with some drives and some stuff like that. And frankly, their capacitors resonate like crazy. So, I tell them, I'm like, not only are you not saving energy, you're probably going to make things really bad here.
Yeah.
And, so again, having distributed capacitors without having sort of the benefit of, knowing what that's going to be it can be problematic.
Yeah, absolutely. Absolutely. All right, cool. So we covered a lot of the bases. What are we missing? Are we missing anything else? I mean, it looks like we had some good questions that we answered. Felix gave us the thumbs up, so that's good.
Yeah, I think those are the main things. Again, if people sell power quality things because it's hard to sell them as actually what they do. Like a harmonic filter really does work, and it works well.
Yeah,
I can get rid of my harmonics, but if I sell it as an insurance policy, people don't want to buy it. They want to buy it as an energy saver. Then you have a real financial justification, right?
Yeah. So are we opening up? Are we doing more at the Experience Center? What's going on in that regard?
Yes. I was in Houston earlier this week, and we're open up down there. We're open up here in Pittsburgh. We're starting to bring customers back in and our own people in for training. And one of the things I tease about, I said last year, I used to tell my boss, we get 7,000 or 8,000 people a year through here, and I said if I didn't have people coming in, customers coming in, we could get so much more done. So he said last year when we weren't working, and stuff, and we were still here. He's like, you better get a lot done this year. So we added a bunch of new demos. It's pretty cool, some neat stuff. So yeah,
that's cool. So what from a demo perspective, what do you think is the most intriguing one?
Honestly, like this is still one of my favorites to talk about.
Yeah.
But we have the microgrid. We have a harmonic resonance demo where we built, like, on purpose, we created resonance. We have a water analogy one, again, to explain to non-electrical people how electricity works.
Yeah.
Variable frequency drives demos. Again, lots of cool stuff that are even like the one of the things we could talk about at one point is maybe one of the breaker demo you saw. You helped us design that one. Actually, that would be a good thing to talk about. Just just simple stuff with actual breakers. There's just a ton of things we're working on, and it really is kind of a fun kind of environment to learn this stuff.
Absolutely. So James Smith is asking, where do you place the capacitors? Next to the harmonic device, at the bus, etc. So what about placement of the capacitors?
If you make them into a harmonic filter, let me just switch over here a second. So if I have and let's say I have another transformer, and I have my drives or whatever my harmonic loads are that are producing harmonics, right?
Mm-hmm.
So let's say I want to create, if I put a capacitor here, or if I put a capacitor here, I'm going to have resonance. This capacitor will resonate with this series combination of inductance. This capacitor will resonate with this transformer. If I make them into harmonic filters, I want to put that filter at the lowest level that I can, close to the load in this regard, because I want to absorb that current before it goes up through the transformer. When I say absorb, again, it goes out on phase A, goes through this, goes out, goes back on B and C. So the harmonic current just gets exchanged here in this loop. If I don't have a filter here, the harmonic current flows up here, maybe even all the way back to the source, somewhere back in the source, and flows back down through the system and so forth. So if I put a harmonic filter here, what I'm doing is I'm pushing harmonics up through a transformer, and here's Ohm's law. Remember all these things we talk about, but basically voltage distortion equals current distortion times harmonic impedance. So if I push my harmonics through here, I'm going to screw up my voltage here.
Right.
If I put my harmonic filter here, my impedance is basically zero, so I don't get any voltage drop by putting that there. So the closer you put the harmonic filter to the load,
Mm-hmm.
less voltage distortion you'll have.
Right, and voltage. The importance of the voltage distortion is if you distort the voltage, now you're impacting a wider area in the facility, right? From the power distribution system.
So harmonics are a two-part problem. One is current distortion, pushing current up through the system and causing heating. The other one, like you said, was if I screw up my voltage, if my voltage is supposed to be nice and clean, but I have sort of flat topping or whatever, something bad,
Yep.
then everything on my system takes that voltage and uses it, on my other loads. Even if it was a linear load, linear being resistive or whatever, my current is going to look just like my voltage because it reflects voltage. A misoperation usually occurs with voltage distortion, where heating usually occurs with current distortion.
Okay, so what if I had variable frequency drives further up in the system on the line side of that second transformer that you have up there?
Here. Yeah. So let me just, I'm a little too messy.
Yeah, let's get a clean piece of paper here.
Clean piece of paper. Tom, while I'm drawing this, one of the things I talked about in my presentation I'm doing for next week was, people like to draw on the back of it. We always say on the back of an envelope, and one night I was at home, I was talking about one side that goes to Pitt. I was literally drawing on the back of a pizza box. I'm like, engineers love to draw on anything.
That's right.
It was just, but in this case, it got a little messy there. So yeah, so say we have our harmonic source here pushing up through the system, but say we have one here, so we have a drive here. So the interesting thing about that is, let's say you have a capacitor here, okay? This drive, from its perspective, from its eyeball, looking at this inductor in series with that capacitor, might look like a harmonic filter, might be the low point here. Because if I have an inductor in series with a capacitor, and I have J10 minus J10, guess what that impedance is? That impedance is zero. So if I have my harmonic current source, that current wants to flow there.
Yeah.
And if I'm not set up for it, I could overload that capacitor. So a series resonant problem could occur there, or a parallel resonant problem could occur if I have a capacitor in parallel with another transformer. Yeah.
So you would typically model the entire system and let the software do the analysis for you, right?
Somewhat, yeah. And the nice thing about harmonic analysis is it's a lot like some of the simpler short circuit analysis where you don't need a lot of buses. You only need a few buses because most of the impedances here, in the transformers, the cable lengths aren't going to add that much to it. It'll change a little bit, but yeah. And then it's really all about where you place the capacitors to figure out what's important.
Right. Well, that was a good question, James. That's I never really thought about the complexities of that and where you're putting the capacitors in relation, and then like you say, filters, and you got to tune that filter, pick the capacitor that you want, and the inductor. So that's an analysis that needs to be done. And you used to go out and find these problems, right? So somebody would probably call and say, "Hey, this piece of equipment just failed. Why did it fail?" And then you go out to the site and
I keep blowing my fuses on my capacitor, and I replace them, and they just blow again.
well,
well, maybe you shouldn't replace them. You might
well, no, Busman loves
I know
that.
it's okay. Here, it's okay, Tom. We'll be okay. It's really important that they replace the fuses over and over and over again.
There you go. There you
There's
go.
Tom. See the resemblance there on the screen? I like that. So there's you on the right
Yeah.
and you on the left. That's it. That's a good. If anybody hasn't seen that video, they got to watch it.
Yeah, I put the link out. I shared the link out with everybody, so you got to check that out and see. I still say the referee was blind. I'm telling you.
I don't know.
Yeah.
I think clearly the breaker won. I agree. I agree. The breaker won.
I don't know about that.
And then there's Eric. He's like, cheating. He was like,
And
I think he should have.
Eric should have jumped on my shoulders because I can give him 200,000 amp in a short circuit current rating.
I know.
The breaker's not going to do that for him. Felix.
Okay. We got him through.
Felix pointed out that we should probably, and you know what, Dan, we've got to find some time and do a power quality and just try to figure out a good program. And it's probably a serious, the hard part about power quality from an educational perspective is how do you pare it down to bite sizes?
Yeah.
That's the challenge. And
I think that's the challenge. And I think, but you can simplify sort of the topics, right? So you could talk harmonics, which we did a little bit of, and it's kind of related to power factor. And then you could talk voltage sags, which in voltage interruptions and stuff. So like that part of it. And then the other part that's important and kind of a separate subject is transients. So like high frequency surges and lightning strikes, stuff like that. And then really the fourth part is grounding. But if you can understand those four topics, you kind of break those down. That's so we have a lot of other videos on that same YouTube channel or on the website. Yeah. So if people look on there, there's a number of videos on those topics, and there's one on power quality case studies, which goes through 6 different things or 8 different.
Yeah. So, and that's the other thing is if people go to that link that I shared, they will be able to they'll be able to see all the other videos, and they can just they can search on a lot of these different just navigate through. There's a bunch of cool things that you guys have done up there at the Experience Center. But we're gonna have to sit down and think about putting something together. Izzy on YouTube says large hospital research center had variable frequency drives on every motor, 5 horsepower and larger up to 50 horsepower, 60 horsepower and higher had 18 pulse VFDs. The higher the pulse, the better, right? Yep. Do the 18 pulse drives solve any energy or less trouble with harmonics?
It's mostly just less trouble with harmonics. When you, I'll say, so a 6 pulse drive current looks like this.
Yeah.
And if you look at the frequency spectrum, you have a fundamental, the first harmonic, and then you have 5th and 7th, and you have 11th and 13th, and you have 17th and 19th harmonics, and so forth. An 18 pulse drive, literally the current has 17 little blips in it. And so if you look at which harmonics it has as a fundamental, and then it has 17th and 19th, then 2 times that, and so forth. So all of these extra harmonics that aren't flowing through the system now, again, what is that? That's I squared R losses. So if you believe, going back to our premise that I squared R losses can save you a little bit, 1 to 2%, it's not a bad thing to eliminate that, right? So
Right.
so 6 pulse versus 18 pulse, yeah, you can save some. There are going to be a little bit of transformer losses, but at the end of the day, you're at least equal or better with the 18 pulse. Now, the fundamental, that's the part doing the work.
Yep.
That doesn't change, right? I mean, again, it's a little bit of I squared R losses, but it's not going to change much.
So would you have less of a chance for series resonance or parallel resonance types of issues?
Yeah, for sure. If you do the math, with that transformer and a capacitor, if you do that square root of short circuit kVA, I don't know if that's on the screen, yeah, divided by the capacitor kVA.
Mm-hmm.
You do the math for that, and that's the frequency of resonance. Think about it, the bigger the capacitor, the smaller the resonance number.
Right.
So what happens is you have this sort of parallel resonance that kind of goes like that. And so the bigger the capacitor, the smaller the resonance number. So if I didn't have a big capacitor, sure, I could hit way out here, but the capacitor is so small that it's not going to amplify a whole lot either. So the benefit of having small capacitors is that you're going to amplify harmonics that aren't very, very big to begin with, and they're not going to amplify much. If I was hitting down here around the 5th or 7th harmonic, now I have a potential issue, and that's the real issue there.
That's cool. That makes sense. That makes sense. So now those drives are probably more expensive, obviously, but you're avoiding a lot of issues that you could possibly have in the power system.
Yeah, and that reminds me too that I didn't bring this up earlier, but we have 27 videos that are on our. If you go to Eaton's YouTube playlist, there's a FAQs for harmonics, and we talk about 18 pulse. We talk about a bunch of different things, and I think in the first 10 videos or so, I go through a number of different solutions. So yeah, that would be worth looking at, and it kind of explains how much better they are and how much different they are. And then we also just recently wrote a paper. It's going to be out on our website at eaton.com/harmonics. Should be out in the next few days, but it's like literally like a 25-page paper on like a tutorial on harmonics. So that would be something, Tom, worth sharing as well.
Yeah,
it's not done yet. I think it's in the next few days it'll be out, I think.
Yeah, so if I'll just eaton.com/harmonics, and they can just monitor that. I mean,
look for it in the next week or so. I think it'll be out.
Yeah, and then and I'll make sure that when it comes out, let me know, Dan, and I will share it with everybody. I'll just, what I do is I just press this little button, and it goes live on 5 different channels, and I say, "Hey, everybody, here's some stuff, some new stuff for you," and we're all good. So, yeah, in fact, that sounds cool. So I think we covered a lot of good stuff, and we'll set up some time in the future to do some more on power quality, and maybe we separate it, like you said, those 3 sections: voltage sags and swells, transient events, and then the whole harmonics. Yeah. Yep. Well, cool beans. Well, I think I'm pumped out. Don't go to I don't know what that means. So thanks, everybody. I mean, unless there's anything else, is there anything else you want to cover?
I mean, I think there's a million things we can cover.
I know.
I think it's good. I think we covered. The main thing is just what's interesting about false energy savers. I'll leave y'all with this: is talk to people about it. And what you're going to find out is there are a lot of people that have experienced this that you probably don't know about. There's a lot of even some news channels and TV shows and stuff that I've seen, and it's unfortunate because it just gets spread, the word of mouth. So if people are on this call and they know that maybe one of their friends got involved in this, it's probably worth bringing it up to them to make sure they understand it.
Yeah, and raise awareness, raise your level of knowledge, ask those hard questions, and don't settle for the easy answers.
Right.
So Tamaki, thank you. Chris Jensen, I appreciate you dialing in, brother. Mike Solo, Felix. We had a lot of good people out there, and a lot of great questions. Robert from Omaha, awesome, and Izzy Garbo. Thank you for joining in. Thanks everybody for tuning in. Hang on 1 minute. Hang on 1 minute there, Dan, and I'll sign everybody off. And so another interesting Steve Froming in the house. So thanks for joining in. Okay, everybody, we're gonna shut down this feed. Take care, and next week, Dan, I'm taking a vacation week, so I'm probably not going to stream all next week unless I really have something to say that's huge. I highly doubt that. So take care, everybody. Stay safe, and remember, please stay healthy. So I'm going to cut there, and remember that guy.
There you go.
All right. Okay. Take care. Oh wait, Tamaki says, last thing, are harmonic filters and reactors the same things sometimes?
A lot of people use the term harmonic filter when they're really just talking about a reactor. And a reactor, there's one of those frequently asked questions. It might even be the first one, is what is a line reactor or a DC choke? It truly constricts the flow of current from flowing down the line. It doesn't allow it to flow. It's kind of like if you take a water hose and you pinch it or squeeze it,
Right.
It doesn't allow the harmonics to come out of the load. So it's a little different than a harmonic filter. What a harmonic filter does is redirects the current and goes back to the load. So again, current, what we think of constant current sources is totally different than what we think about for most things, which is voltage sources. Current sources have to flow in a loop. They have to start and end. By putting a choke or a line reactor, it constricts it, so it never allows it to start. So 10 amps versus 5 amps or 6 amps or something.
Okay.
Like that. So it's different, but worth watching that video, and I think it'll make more sense.
All right. Cool beans. Okay. That's the last one. We're done. Thanks again. And you know, this is what I do all the time. I end like 5 or 6 times. So that's it. Thanks, everybody. Thank you, Dan, for taking the time out. I really appreciate it.
Thanks, Tom. That was fun.
Yeah, always good discussion. Thanks, everybody, for tuning in. And we will probably not see you next week, but we'll see you the week after. Take care, stay safe, and please stay healthy. All right. Great job, James Smith.